Yeah, this is indeed part two of When Space Reaches Down and Touches Us, a not so short guide to cosmic catastrophes. If I imagine a bunch of you have seen part one. If you haven't, it's up on the Mount Cuba YouTube channel. And just a quick reminder of what we looked at last time. So in the first part of the first talk, we considered comets and asteroids and the threat that they pose to us. And this is a relatively well-known one, I think. Everyone sort of thinks about, the asteroids wiping out the dinosaurs, or, sometimes wishes for a giant rock from space to come down and end it all. But one kind of cool thing that I went into during the talk was to talk about how a comet swarm may have been responsible for the Younger Dryas climate excursion about 12,000 years ago after the end of the Ice Age. And then in the second part, we looked at the prospects for a super flare from the sun wiping out the global electrical grid and plunging us all back into the Iron Age. So those are both threats from inside of the solar system, from the very local environment. But, there's a whole universe out there. And it turns out that it can be pretty dangerous as well. So, let's consider the threat from the stars. Now, our own sun is about middle-aged, and in 4 billion years or so, when it exhausts the hydrogen in its core, it will blow up into a red giant, and that red giant will fry the Earth and maybe even absorb the Earth and destroy it entirely. But of course, this is not a particularly imminent threat. After that time, the sun will leave behind a white dwarf, which is kind of a slowly cooling ember, a spent stellar core with no fusion happening. Now, our sun is a relatively small star. It's a G-type star. You can see that on the left over here. You can see how small it is compared to A, B, and especially O-type stars, which are absolute beasts compared to the sun. They're 10 to 50 times as massive as the sun and can put out anywhere from a few hundred to a few 100,000 times the amount of energy that the sun puts out while they're burning during their lives. But when they die, they don't turn into red giants and leave behind a white dwarf. They catastrophically explode in a supernova. So this is a massive explosion that puts out something like 10 billion times the amount of energy that the sun releases. And it, of course, a lot of that energy is very high energy light, so you get a lot of ultraviolet light, you get a lot of X-rays, and you even get gamma rays. The supernova also accelerates matter, charged particles, electrons and protons, up to very close to the speed of light. And this gives rise to a phenomenon called cosmic rays. And cosmic rays are constantly hitting the Earth, hitting you every second, in fact, and you never notice because they're rather tiny. But they're a significant source of energy. Now, there's always sort of a general background of cosmic rays from all of the supernovae that have gone off before. And, it's not particularly dangerous to you, but if a supernova were to happen close enough, and that's been calculated to be about 50 light years away, which when you consider the galaxies 30,000 tens of thousands of light years across, 50 light years away is sort of pretty much in our backyard. So a supernova has to happen pretty close by on galactic terms to actually be dangerous. Now, you might imagine that there's this big shock wave that comes out and sets the Earth on fire or something like that, but that's not actually what happens. So the high energy photons that are coming in, all of those ultraviolets and X-ray photons, will strip away the ozone layer of the planet, which then exposes us to the ultraviolet radiation from our own sun. And that is, of course, a major health risk. Those photons will also ionize the oxygen and the nitrogen in the atmosphere, and this can lead to the formation of nitrous oxide. Nitrous oxide will block starlight or sunlight. So you get a kind of smog covering the planet. And then those cosmic rays that I mentioned. So when cosmic rays enter into the atmosphere, that also ionizes the atmosphere, and that leads to cloud nucleation. So you basically get, if you have a lot of cosmic rays coming in, you get more clouds forming at low altitudes. And if you have a lot of clouds and you have all this nitrous oxide, and they're both acting to block sunlight, then the temperature of the Earth will drop, and you could enter into an ice age, which can be pretty bad for anything that does not like cold weather. And of course, all of this high energy radiation, all of these cosmic rays, all of the UV from the sun, which is being let in through the ozone layer, can lead to a higher mutation rate and can cause cancer, which is maybe a problem if you're a bacterium, but if you're a whale or a brontosaurus or any other large organism, and the number of cosmic rays hitting you is much higher, and the chances of you developing cancer are that much higher. So this is more of a risk for your large, complex life forms. Now, there are actually two kinds of supernova. We were just talking about the ones that come from massive stars, but there's another type. So the massive star supernova, these are type 2 supernova or core collapse supernova. And the reason these happen is that as the star is, during its life, it's fusing material in its core into higher and higher elements. So it starts out with a core made up of hydrogen, and that gets fused into helium, and that fusion releases energy. And then the helium fuses into carbon, and that releases energy. And the carbon fuses into nitrogen, I guess, and that releases energy. And that sort of continues on up and up through the periodic table until it gets to iron, which you cannot get energy out of iron fusion. So some of the iron will still fuse, but there's no more energy being generated from that. So once you have an iron core in one of these stars, there's no more energy being produced in the core. Now, the star itself is held up against its own gravity by the pressure from the radiation being released from the fusion in its core. So when it reaches this state, there's no more radiation pressure coming out to prop up the star, and the star then collapses very, very rapidly. And that sudden collapse leads to the explosion. Massive stars, the ones that make supernova, type 2 supernova, are pretty easy to find. If you look up in the night sky, most of the stars that you see are massive stars. Even though they're only a small fraction of the total number of stars in the galaxy, they're so much brighter than any of the other stars that they can be seen a very, very long way away. And this is good for the whole supernova threat question, because it means that we have a relatively easy time identifying the objects that are likely to turn into a supernova. Now, the closest type 2 supernova progenitor that I'm aware of is Betelgeuse. And, well, maybe not the closest massive star, but certainly the one that's in a state where it is likely to go boom relatively soon. By soon, we mean sort of probably in the next 100,000 years or so. Now, you might remember, I guess about a year ago now, a little over a year ago, there was stories in the news about Betelgeuse kind of acting up. It suddenly got a lot dimmer, and they'd never seen Betelgeuse behave like that before. It's a highly variable star, but they'd never seen a dimming like that. And this led to a lot of speculation in the media that, oh, maybe Betelgeuse is going to go supernova. Maybe, it didn't. It turns out that the most likely explanation is that a large cloud of dust was expelled from the star along our line of sight and blocked our view of the star for a month or so. In any case, Betelgeuse is about 600 light years away. So when it goes supernova, it will be a bright light in the sky, I think sort of comparable to a full moon, but it will not be dangerous in the slightest. Now, a type 1 supernova is a rather different beast. So these come from the white dwarf stars, just like our sun will turn into. And they detonate when they reach what's called the Chandrasekhar limit. So this is an upper limit on the mass of the white dwarf. It's around 1.4 solar masses or so. The reason that happens is the white dwarf is basically a big ball of carbon. And it's held up by electron degeneracy pressure. Don't worry too much about what that is exactly. The reason for the 1.4 solar mass limit is that when you reach that mass, the electrons, so that as the electron degeneracy pressure goes up, the electrons start moving faster and faster and faster. And then once they hit 1.4 solar masses, they're moving at the speed of light, which is impossible. At that point, the star, no more electron degeneracy pressure can be created, and the star collapses in on itself, igniting carbon fusion almost instantaneously, and the star explodes. This is most of these happen in binary systems, such as the one depicted, where you have a white dwarf star and an evolved normal star that it's turned into a red giant or something like that, and the material in the outer atmosphere of the giant star gets far enough away from the center of gravity of that star that it is no longer being held to that star, and it falls into the gravitational influence of the white dwarf star. It spirals in onto the white dwarf star, collects into an accretion disk, falls onto the surface of the white dwarf star, and when the mass reaches 1.4 solar masses, it goes boom. So white dwarf stars in general are tricky to find because although they're very hot, they're really tiny. They're about the size of the Earth, so they're extraordinarily dim. The brightest white dwarf stars that you'll find are about 1/10 the luminosity of the sun, and they can go down to about 1/100,000th of the luminosity of the sun. So they're a little trickier to find, but we think we know all of the nearby white dwarf stars. We think we found in particular the really dangerous ones are the ones in binaries, because of course a white dwarf star that's just sitting there alone in space its mass isn't going to change, so it's not a risk for a type 1 supernova. And the closest type 1 supernova progenitor is a star IK Peg, which is about 150 light years away. So again, we seem to be in the clear right now. Because that's well beyond that sort of 50 light year danger zone. But that, the sun is moving through the galaxy, so its local environment is changing. So, things are, and all the stars are in the galaxy are moving as well. So, it's not always the case that we're so safe. And some estimates have been made of how often we do get a supernova close enough to do damage, and those range, depending on the models, from anywhere from once every tens of millions of years to once every few 100 million years. So given that the Earth is about 5 billion years old, you would expect that this has probably happened more than once. And it's also worth noting that it's not random. So an important thing about the massive stars, in particular, that give rise to type 2 supernova, is that they're very short-lived. The sun will live for about 10 billion years, but a massive star might only live for a few million years before it exhausts its hydrogen and explodes. And for that reason, they're typically found close to where they're born. In particular, that's in the spiral arms of the galaxies where you find most of the dust and gas from which stars are made. And that is why when you see a picture of the spiral galaxy, like our Milky Way, you'll notice that the spiral arms are typically very blue, because that's where all of the massive stars are. They dominate the light coming from those parts of the galaxy. So the sun orbits the galaxy about once every 250 million years. It's referred to as a galactic year or a great year. So, one great year ago, I believe the dinosaurs still had not evolved. During the course of that orbit, the sun will pass through spiral arms and then pass between spiral arms. And as a result of that, its supernova proximity risk is strongly variable with time. So now you're wondering, well, what does that mean for us now? So right now, the sun is in something called the Orion Spur. That's this structure here. And that is a kind of minor spiral arm. It's not a full spiral arm, but we are in a somewhat elevated period of risk compared to if we were, say, between the spiral arms like this. If you get a little closer to the sun, you find the sun is actually inside something called a local bubble. So in the immediate vicinity of the sun, there's the local cloud, which is kind of shown here. But around that local cloud, a little bit further out, is the local bubble, which is this large region of interstellar space, which it has a much lower density than the average. So it seems to have been cleared out by something. And the most logical, most straightforward explanation for that is that it was the shock wave of a nearby supernova that cleared out this bubble sometime a few million years ago. So I mentioned that iron is the last element which is produced by core fusion in massive stars, right? So I just want to emphasize that point because it's pretty important. Now, most of the iron that's produced is what we call iron 56. It's an isotope of iron that has an equal number of, no, not an equal number. It's got 26 protons and 30 neutrons. And that's a very stable isotope of iron. So the overwhelming majority of the iron on the Earth, it all came from supernova. That's the only way to make iron is in the core of a massive star, and the only way to distribute it through the galaxy is from a supernova. So all of the iron on the Earth came from supernova originally, but it's all iron 60 because that's the stable isotope. But there are other isotopes. So there's, it's all iron 56. There's other isotopes like iron 60, which are radioactive. They are not stable. So the difference is that this has 4 more neutrons in the nucleus than iron 56 does. And the half-life of iron 60 is about 2.5 million years. So if you find any iron 60 on the Earth, this tells you that it cannot have originated locally. It must have been recently manufactured in the core of a massive star, and it must have been recently arrived on the Earth, because otherwise it would simply be gone. And as it turns out, we actually do find a little bit of iron 60 in sediment on the Pacific Ocean. Actually, so this is what I had before I saw the colloquium a couple of weeks ago. It turns out they've now found this signal in several sites all over the Earth. So this is a very well replicated signal. And so this is what you're seeing here is the ratio of iron 60 to ordinary iron 56, as a function of time, millions of years before the present. And right here around 2.5 or 3 million years ago, there's this very strong spike in iron 60. And they could actually use that to even determine how far away the supernova was. Just taking the half-life of iron-60, the amount we find here on Earth, they can sort of do the calculations with that. And it turns out that this supernova was certainly, it wasn't like really close, but it was within the kill radius. It was close enough to do some damage. Not a lot of damage, but close enough to do a little bit. And, 2.5 million years ago, there weren't any proper humans, but our distant ancestors, the Australopithecines, would have seen this in the night sky. Now, interestingly, this time also corresponds to the end Pliocene extinction, where a significant, it wasn't one of the great mass extinctions, but a large number of megafauna, marine megafauna in particular, went extinct around this time. One of them was, I think it's called Carcharodon, this giant shark that had been around for a really long time. So that, and it's been suggested that this is directly connected to the supernova, which was not close enough to, cause a real mass extinction. Obviously, our ancestors were here and we're here, so it didn't wipe out everything on Earth, right? But apparently the marine megafauna that live in near surface environments would have been a little bit more subject to some of the climate effects, the weaker ozone layer, for instance, and thus maybe went extinct because of the supernova. It's also been suggested that the first large, or maybe not the first, but one of the massive extinctions that happened in the Devonian 360 million years ago might have been due to a supernova as well. This is based mostly on the fact that there was an ice age around that time, and that the fauna that went extinct were again mostly in a near surface marine fauna, whereas fauna that was organisms that lived deeper in the ocean were spared, I believe. So, but that's it. This one is more speculative. No signal has been found. Of course, finding a signal from 360 million years ago is trickier than finding one from like 2.5 million years ago. Now, some of the really big supernova, the largest ones, will sometimes give rise to something called a gamma ray burst. So this is a type of explosion where a large fraction of the energy actually gets beamed out along the star's rotational axis. And of course, because it's being beamed, that energy then travels, remains coherent over a much longer distance than a spherical supernova shock that will fall off in intensity much more rapidly. As a result of that, a gamma ray burst can be dangerous out to several thousand light years away. The kill distance, if we're right in the path of a gamma ray burst, they can kill us from across the galaxy. It doesn't have to happen in our backyard. But they're directional, so they need to be aimed directly at us, right? So it could also be that a gamma ray burst that goes off relatively nearby but is aimed in the other direction does no particular damage at all. It all sort of depends. And of course, the chance of it being aimed directly at us is, pretty low for a fairly narrow beam. So the probability that the Earth has been hit by a GRB over the last 4 billion years is something like 90%. And it's about 50% within the last 500 million years. And in fact, it has been suggested that the end-Ordovician extinction, which was the second largest mass extinction, I think, and I think also the first of the mass extinctions that we know of, may well have actually been caused by a gamma ray burst. This is the one where the trilobites went extinct. So a lot of other things went extinct too. marine species in particular, and mostly again, the near surface ocean environment, were the ones that went extinct. Now, one of the, I think there was also, yes, there was a sudden ice age. So I should back up a sec. The sort of immediate consequences to a gamma ray burst are very similar to what you can get from a supernova. Ozone stripping, cosmic rays, ice age, nitrous oxide production, again, ice age. The main difference is that it can do this from further away. And so there's a sudden ice age. I think might have been something else as well. I think the main thing was just where the extinction was localized, specifically which species were going extinct, and the fact that there was an ice age attached where they think it was. They haven't found any isotopes or anything, which again are tricky to find. Of course, it doesn't necessarily end with a supernova. Some stars can continue to be a bit of a threat even long after they're dead. So some fraction of massive stars will end their lives as neutron stars. So this is, you can think of a neutron star kind of along the same lines as a white dwarf. It's the spent core of a massive star because it's much more massive than a white dwarf. Its gravity is stronger. Electron degeneracy pressure is not sufficient to hold it up. It needs neutron degeneracy pressure. As a result of that, it is even more compact than a white dwarf. So as a white dwarf is about the size of the Earth, a neutron star is about the size of a large city, but still packs in the mass of a star. And they spin extraordinarily rapidly. They rotate on their axes sort of once a second to even once every thousandth of a second in some cases. And they can have pretty strong magnetic fields, which lead to radiation being beamed out along the rotational or the magnetic axis of the star. So then as it rotates, you get this kind of lighthouse effect, which can be detected as a pulsar, which is how we know these objects are there. Now, some fraction, think about a tenth or so of these neutron stars have magnetic fields 1,000 times stronger than the average. And these are called magnetars. So just to give you an idea, what do I mean when I say 1,000 times stronger? So that works out to about 10 billion times the strength of a magnetic field inside an MRI. And if anyone here has ever taken an MRI, you are not allowed to bring metal anywhere near these things, because if you have some, it will rip it right away and possibly do quite a bit of damage. So, from across the room, right? So think of a magnetic field that strong. Now think of a magnetic field 10 billion times that strong, only it's held by an object the size of a city, and that is a magnetar. So that is a really ridiculous amount of magnetic energy locked into that magnetic field. And every once in a while, those magnetic fields will just spontaneously reconnect with themselves, or just spontaneously relax. So you can think of it like it's the magnetic field is in a certain configuration, and it wants to be in a simpler configuration. Ultimately would like to be in a pure dipole, the simplest possible configuration. It's not quite in that, but it wants to get there. So every once in a while, it kind of relaxes a bit towards that, and so it reaches that lower energy configuration, and this leads to something called a starquake. And in a starquake, huge amounts of energy are released. So this is a magnetic reconnection phenomenon, where the amount of energy that's being released is sort of proportional to like the square of the magnetic field energy or the magnetic field strength. And this can put out, we actually observed one of these back in 2004, Sagittarius 180620. And this is the brightest gamma ray source ever recorded, at least up to that time. I haven't checked to see if it's still the brightest. I think it might even still be the brightest we've ever seen. It actually whited out the detectors of the gamma ray telescopes that have recently been launched, it happened 50,000 light years away, but released an amount of energy equivalent to the sun's entire output over 150,000 years. It's actually more energy than a supernova, but all in the form of very, very high energy photons. So that was 50,000 light years away, right? That was on the other side of the galaxy. But the Earth's ionosphere responded to it. It actually moved lower for a few hours as a result of getting hit by this huge wave of energy from the other side of the galaxy. It was described at the time like the ionosphere ringing like a bell. Oh, the kill radius for a starquake is, I think, a little bit further away than for a supernova, but not a lot. And luckily, there's very few of these objects known. You can see, I believe, all of the ones in the Milky Way noted here. And the closest known one is about 9,000 light years away. So it's unlikely that a starquake will wipe us out anytime soon. But there's a lot of time between now and the end of the sun's life and its journey around the galaxy. We have many, many orbits to go. So they're very rare. I said 10% earlier. That was wrong. Sorry. 1% of them are magnetars. And it seems that like those really strong magnetic fields decay very quickly. So you know, it's born, it's got a really strong magnetic field, you have a bunch of starquakes, lets off all that energy, and after a while, it's an ordinary neutron star again. So even though over time, the galaxy is going to fill up with more and more neutron stars, because every time a massive star dies, it leaves behind either a neutron star or a black hole, and once that's there, it's there forever. The magnetars themselves don't last very long, so hopefully it won't become more likely for us to run into a starquake and get fried by that anytime in the future. And the main point I really want you to take away from these two talks isn't that we are in imminent danger of being wiped out by the threat from space. Because we're not, frankly. When it happens, it's spectacular, but it doesn't happen very often. No, the key point is that space is not just something out there, something up there, something separate from us here down on the Earth. The Earth is in space, it's surrounded by space, and it regularly reaches down and touches us. We are not a closed system. So, you know, in many ways, we're already in space. And that is what I wanted to say today.